Hi, my name is Mike Ivanov. I am an AI hardware architect at IVA Technologies. We develop FPGA and ASIC solutions for AI acceleration and help our clients to get an advantage over GPU-based solutions. Even if you feel you don't need to replace GPU with something less power-hungry and more responsive, I believe you haven't heard how inefficient GPUs are actually. I'm going to tell you about solutions for clouds and data centers. Many of you have heard about FPGA boards, but many don't understand what it is, how it works, and why it is needed. Those who were interested found some open source projects on GitHub, in other places, some ready-made solutions offered by vendors. But these solutions are either raw or slow to work, cover special cases, and are not suitable for you. Many people are repelled by the fact that this area requires specialized domain expertise, special languages, and high entry price. And it is considered that there is no point in climbing here. There is an opinion that this technology is not available to everyone, and I want to convince you otherwise. If you are doing a real-time NLP task, how many of you need to reduce latency? If you are developing a real-time image search or super resolution, how many of you lack good performance while maintaining low latency? If you are a data center, how many of you need to reduce total cost of ownership? Many tasks are not even discussed due to the GPU's technical inability to work with maximum performance on minimum batch size with minimal latency. For example, video calls with image enhancement and super resolution. If you make a CV model on ARM with NPU, are you delighted with its performance? In all these tasks, FPGA and ASIC can help you. Don't think about the complexity of developments. FPGA vendors have already solved a lot of problems and are solving more and more. There are already solutions to such problems as C-nonce and R-nonce inference, SSL and TLS encryption offload, regexp processing offload, images and video resizing and transcoding, SQL databases offload, SQL databases acceleration, memcached acceleration, gradient boosting acceleration, SmartNIC and deep packet inspection. What is an FPGA? On the one hand, it is something similar to the GPU. It's a kind of acceleration programmed in a special language. But the closest analogy is a reprogrammable ASIC. In general, an ASIC is a custom chip that can only perform a function that is embedded in, let's say, compiled from System Verilog language. In the FPGA, you can change its hardware program. This flexibility is not free. If you compare any specific task, the ASIC for this task will be more efficient in terms of consumption and performance. But you can't reconfigure it. And the ASICs are manufactured in relatively large volumes. You can't produce 100 chips, then each piece will be too expensive. Reconfiguring an FPGA from one firmware to another takes a millisecond. For example, your FPGA card was used in cloud transcoding in a Netflix-like service. Users have gone to bed, the load has dropped, and you can reconfigure FPGA for a different task. Another example. Again, let's assume you are a Netflix-like service that recodes or transcodes a lot of video streams in real time, and the load is high. Suddenly, the load increases even more. So what should you do? You can reconfigure FPGA cards from one firmware that handles, for example, 9 video streams to a firmware that handles 16 video streams, but with lower codec quality. You slightly dropped the quality, but avoided denial of service. Now let's return to the inference of neural networks on FPGA. There are several scenarios. The main two categories are real-time applications and non-real-time applications. One of the vendors offers ResNet50 inference at 3000 FPS with batch size 1. With NVIDIA T4, you can get up to 5000 FPS, but it will be at a large batch size. With batch size 1, NVIDIA T4 gives us only 1000 FPS, 3 times lower than FPGA. The advantage of FPGA and ASIC is that you can get high performance on the smallest batch size. As you know, the main computational load for inference falls on two types of layers: convolutional layer and fully connected. Convolution is a matrix-matrix multiplication, and fully connected is a matrix-vector multiplication. So, from a mathematical perspective, the convolutional layer without batching is something like a fully connected layer with batching. So it gives us three categories. Convolution with batching. This type of layer is the best fit for the GPU. Convolution without batching, which is equivalent to fully connected with batching, and fully connected without batching. By the way, all RNN cells, I mean LSTM and GRU, have fully connected layers inside the cell. So I refer the RNN cells to the same category. Why is this happening? There is a computable metric called operational intensity. Sometimes it is called arithmetic intensity. It equals to the number of arithmetic operations divided by the data transfer amount required. For multiplications of large matrices, we have sizable operational intensity. It means higher internal data reuse, so we need less memory bandwidth for this. For multiplications of smaller matrices, operational intensity decreases, data reuse decreases, and more memory bandwidth is required. For matrix vector multiplication, matrix coefficients are used only once, and memory bandwidth becomes a bottleneck. FPGAs and ASICs can perform such operations without batching, as fast as with batching. So if we look at three scenarios again, you will notice that in the GPU-friendly scenario, I mean convolution network with batching, so convolution in offline, some FPGA solutions are worse than GPU and some other FPGA solutions are better than GPU. In the convolution in real-time scenario, FPGA performs several times faster than GPU. And in the RNN scenario, GRU or LSTM or RNN-T, FPGA's advantage is even more substantial. Now, how can you start using it? Many vendors offer their demos in clouds, Amazon or Nimbix. You can request a demo and see how it works. Some of these demos are based on Jupyter Notebook. It is easy to evaluate them. Summary. We've defined three scenarios. In one of them, the FPGA beats on par with the GPU. In two others, the FPGA is far ahead of the GPU. And today's FPGAs still don't have anything like tensor cores. The new generation of FPGA is coming. In the data center market, there are three FPGA players today. Acronix, relatively new player, Intel with their Programmable Solutions Group, previously known as Altera, and Xilinx. Intel has presented Stratix 10 NX with so-called AI tensor blocks. Xilinx has introduced so-called AI engines, and Acronix has already presented their new 7nm FPGA with so-called MLPs, stands for Machine Learning Processors. All these new blocks are specialized blocks like NVIDIA Tensor Cores. And this upcoming generation of FPGA will definitely leave the GPU behind. This graph shows that over time, the efficiency of FPGA increases and the efficiency of the GPU decreases. Why is this happening? The GPU as a weak point, memory bandwidth. Have you watched CEO NVIDIA Jensen Huang's presentation about Ampere? Volta and Turing have an HBM bandwidth of 900 gigabytes per second. Ampere has 1500 gigabytes per second. It is 1.6 times faster. Now look, its 8 performance of A100 6 times faster than T4, but ResNet 50 inference at A100 only 4.7 times faster than inference at T4. Let's look at training. FP16 performance of A100 5 times faster than V100, but ResNet 50 training and V100 only 2 times faster than V100 memory bandwidth. What is the reason for it? The answer is coarse-grained architecture with shared memory. To compute different convolutional layers, CUDA cores should be combined in different ways using shared memory. This feature of coarse-grained architectures increases the load on shared memory. To work around this problem, in coarse-grained based ASICs, neighboring compute cores are connected directly to avoid data exchange via shared memory. Unlike the GPU, FPGA and ASIC can have any grained architecture. Everything is defined by FPGA firmware and ASIC architecture. So FPGA and ASIC can avoid excessive use of shared memory by design, by the architecture. In summary, the FPGA becomes the new data center champion, thanks to its flexibility, programmability, and lack of GPU disadvantages. Now, if your data center is huge, or if you have a lot of them, then ASIC may be more suitable for you than FPGA. It depends on the load profiles and the required scale of computations. Now let's focus on ASIC. FPGAs and ASIC are similar in many ways in the development flow. Both use system Verilog, and a significant amount of knowledge is shared. But there are also differences. For example, in an FPGA, we are dealing with a specific chip or a selection from a certain list of chips that has already a predefined amount of programmable logic, memory blocks, and arithmetic blocks that needs to be optimally utilized to enable computations with minimum stalls. The development approach in ASIC is different. We determine the memory size, the number of and type of arithmetic blocks ourselves. We define how to connect blocks, which blocks to connect, and what internal data transmission bandwidth is needed. The difference in the ASIC and FPGA development mindset is very significant. That we can easily generate different firmwares from the single code base according to customer requirements, such as latency, performance, non-conventional layers, and so on. For example, we can build 3 different firmwares from one single code base. First firmware is balanced for all CNNs. The second firmware is optimized for 1 or 2 specific CNNs, and some other CNNs may appear not compatible with this firmware. And the third firmware can support all CNNs, but optimized to a number of them. For example, MobileNet contains so-called depth-wise separable convolutional layers. This type of layers has way less computations than classic convolutional layer of the same size. In our current firmware, if our current firmware doesn't support depth-wise separable natively, we can replace it to mathematically equivalent convolutional layer, but it will take tens to hundreds more time to compute than classic convolutional layer. In contrast to the high customizability when developing for FPGA, we should follow one of 2 approaches when developing ASIC. The first approach is when we develop a data center ASIC like Google TPU. In this case, we must support everything, make it configurable at real time, runtime. We can't change its firmware. The second approach is when we develop ASIC for a specific task, for example, for a self-driving car. If our machine learning scientists tell us that depth per separable convolutional layer are the cause of quality drop, then we may not implement depth per separable support in ASIC. That's just an example. In this scenario, hardware-software stack should be co-optimized. Don't implement in hardware something what is absent in CNN models. We should use additional CNN's hardware architecture-aware training. In this case, general-purpose CNNs can work less optimal on the ASIC, but the CNN that was end-to-end optimized will demonstrate excellent results. In addition to that, we can add more blocks to ASIC. For example, 2D image processing, compression, and so on. In summary, ASICs and FPGA skills are similar, but mindset is different, and business tasks are different, and ASIC must be produced in large volumes to be competitive. Now I'll tell you about what we've designed at IVA Technologies. We've developed two ASICs. They use the same programming model, the same architecture. One of them is targeted to data centers to be used in PCI accelerator cards, and the other is a system on chip to be used in edge devices like quadcopters, factory machines, vehicles, and so on. It has additional interfaces, for example, CSI interface to ingress serial data stream from camera, and also it has a CPU and a small GPU inside. We've decided to support as many math operations and layers as possible. We support convolution, LSTMs, GRUs, transformers. We've developed the software stack that includes neural network compiler, which takes model in ONNX or TensorFlow format, and we've developed quantization tool, which converts FP32 model to int8 precision. What we offer: first, boards with a chip. Second, separate chips to be used on a customer's board. And the third, IP cores to be used in customer's system on chip. That's all. Thank you for attention. I would like to answer your questions.